this is negligible, but the most important contribution comes from our galaxy. So one can compute what are the different fluxes. This is again the flux as a function of the energy. This is for a particular case, which is a 4 PeV dark matter, and each of these lines is one decay channel. So for instance, you see this blue line is decaying, dark matter decaying into a pair of B quarks, B and anti-B quark. And well, you have other lines here. So for instance, the green here is the decaying into U quarks, in general light quarks. And you see that all these channels into quarks produce a kind of soft channel, a soft spectrum. So most of the neutrinos peak at much lower energies than the mass of the dark matter. But we can also consider dark matter decaying into harder channels, like for instance gauge bosons. These are W bosons and C bosons. And you see that the spectrum is a little bit harder, so you have neutrinos at higher energies. Or you can consider even harder cases. So you can consider decays into leptons or decays directly into neutrinos. At first order, the decay, for instance, into neutrino will produce 2 neutrinos with energies equal to half the mass of the dark matter, which is basically, just look, for instance, at these lines here. You see that there is this peak here, which is basically a delta at the energy equal to half of the mass. But at this for these very high masses, we are talking about 4 PeV, electroweak corrections matter a lot. So you can have, let's say, electroweak Bremsstrahlung. So you can produce W bosons like Bremsstrahlung or W bosons. And
the assumption here is that the dark matter decay is only one channel.
Yeah, this is just for each line is a single channel. So you have your particular model, you will have to combine these fluxes in whatever branching ratios are for each model. This is just to show the different shapes of each cases. So I said, for instance, for the case of the neutrinos, you have these 2 neutrinos produced with energies of equal to half of the dark matter mass, but you also have a tail at lower energies coming from electroweak Bremsstrahlung of gauge bosons, Ws and C, that produce neutrinos at lower energies. So these are the typical fluxes that you expect. Obviously, you have to. This is taking into account the galactic and extragalactic contribution, taking into account the neutrinos mix and oscillate, so that is also included in here. And basically, what you do with this, you put these fluxes with effective areas of the detector, with all the technical details of the detection that Juan Pablo described, and you see what is the expected event spectrum that you would have in these cases. Okay. This is actually for the energy distribution. But soon after all this works, there were people saying, okay, but we are only questioning about what is the energy distribution, if the dark matter decay can explain the energy spectrum that we see. But obviously there is more information in the detector, so we can try to see if actually the angular distribution that IceCube sees agrees with what one would expect from dark matter decays. And actually, as I said, dark matter decays have 2 contributions. We have the galactic contribution plus the extragalactic contribution. The extragalactic contribution is basically isotropic. So basically the same as one would expect from a typical astrophysical flux coming from AGNs or gamma reverse, etc. However, the galactic contribution, as the name says, is galactic. So it traces the galaxy. So the combination of those 2 contributions means that the angular distribution coming from dark matter decays, mostly because actually the contribution from the galaxy is the most important in the case of dark matter decays, as I just said, is different from a typical isotropic astrophysical flux. So some people studied what is the angular distribution of the events in an IceCube, and studied the compatibility between this angular distribution and in dark matter decays and in an isotropic distribution. And actually there are answers in both directions. So there were some people saying that actually isotropic distribution and dark matter distributions are very similar. Actually, these are, for instance, the Tessa statistic this is for dark matter decay, and this is for an isotropic distribution. The p-values, I don't quite remember the number, but it's something like 18% and 40%. So basically, there is no way to distinguish from the angular distribution right now a dark matter contribution or isotropic flux. There were some other people who just consider the interval between 60 and 100 TeV, where maybe there could be an excess of events given a typical e to the minus 2 astrophysical flux, and they also studied what is the angular distribution of that group of events, and they actually couldn't tell much the difference between an isotropic and a dark matter angular distribution. On the other hand, there were a couple of works which say that, well, maybe dark matter is a little bit better. This is in this work, Trotsky, what he did was consider events about 100 TeV, and well, the data is the red. This hatch line is hatch region is the isotropic distribution, and this dash, I think is the solid one, is the dark matter decay. So this is slightly better, apparently, from this dark matter distribution. Also, there was the paper by Ismaili Khan and Serpico, who did some angular, more detailed analysis on the angular distribution for dark matter and comparing that with isotropic, and they concluded that dark matter decay is slightly more, the distribution, angular distribution is slightly more favored. But I would say this is just a matter of language. It might be that it's a bit more favored, by how much favor it is to say that it's actually better. Maybe all these things are all within 2 sigma, so there is no way to distinguish one from the other at 2 sigma. And I think basically, even if they phrase it in a completely different way in all these works, basically they agree there is no way to distinguish that if your minimum criteria say 2 sigma. So far, so good. There is no way to distinguish astrophysical, pure astrophysical isotropic flux from dark matter decay contribution. Actually, there were many works on that. There were this paper was the first paper where there was an analysis with a dark matter contribution and an astrophysical isotropic contribution. They fixed the astrophysical index to 2, so they assumed e to the minus 2, which is what you would expect from Fermi-Shock acceleration. And then they fit the data to that with the both contributions. Then there were a number of works looking for monochromatic decays, so trying to search for lines in the event spectrum. There were other works here. For instance, in this work they fixed the mass of the dark matter at the PeV range. They considered different channels, and they didn't do an actual fit, but they showed that actually you could explain for different type of models, you could explain the event spectra reasonably well. This work actually they didn't use the Hesse, but they used Messi. Actually, I don't remember if Juan Pablo will discuss that, but this is basically similar to Hesse, but with a lower energy threshold down to 1 TeV. And well, they did the analysis and showing this is for decays into a soft channel, into quarks, and this is the case into neutrinos, and they evaluated what are the values for the lifetime on the dark matter mass that would explain this kind of data better. Okay, so here comes the kind of the multi-messenger part of the work of this problem. So when dark matter decay and produce neutrinos, there is always a flux of gamma rays accompanying those neutrinos. So if dark matter decays into a pair of quarks, as I said before, quarks would hadronize and would produce pions. Those charged pions would decay and produce neutrinos, but along those charged pions, neutral pions are also produced, and those decay and produce photons at this energy gamma rays. And you can think of any possible dark matter decay channel, and you will always have a flux of gamma rays accompanying the flux of neutrinos. And what happens is that we are talking about masses of dark matter of PeV range, and we know that photons with energies in the tens, hundreds of TeV are not, the universe is not transparent to photons of energies of between 10 and 100 TeV, just because of the photons at those energies interact with the infrared background and the CMB and produce C plus C minus pairs. Those C plus C minus pairs then interact with the photons in the medium and basically the CMB, and produce via inverse Compton scattering, produce other photons, and then this is basically a cascade process. And this proceeds until the energies of these photons are of the order of 100 GeV or below, where the universe becomes transparent again, and then these 100 GeV photons coming from these dark matter decays with PeV dark matter decays can be detected in experiments like Fermi. So Fermilab can see those gamma ray photons, and using those, one can set also bounds on the dark matter properties for this in this contest. It turns out that, as I said, these photons cannot propagate very far in the universe when the energies are very high, which are the energy we are talking about. But this happens with, let's say, the cosmological photons, the photons coming from far away from us. But photons coming from our galaxy don't travel that much, so it's a matter of tens of kiloparsecs. And tens of kiloparsecs, the photons don't get completely absorbed even at these energies within our galaxy. And remember, I mentioned that most of the contribution of dark matter decays come from our galaxy. So actually, the application of these limits is not that straightforward as I just mentioned, and actually different absorption occurs for extragalactic and galactic signals. So there was some work in this direction a couple of years ago, and taking into account the different contributions, galactic, extragalactic, the different type of absorption for each, and using the data of like Casimir or Cascade, which are at much higher energies, and using also Fermilab data, well, it seemed to work. They didn't do a fully detailed analysis, but they just saw some cases, and it seemed this was more or less okay. There was a very recent work, actually, well, I think it's less than a year ago, by a group of people where actually the limits, this is the red limit, I don't want to get into the details of this plot, but they saw that actually there might be some tension between some channels and what gamma ray data says. And actually the main problem, as I will show you in a moment, is that for dark matter decaying into quarks, soft channels typically, there are a lot of photons which are produced. So these are usually the channels that have more problems with gamma ray observations. On contrast, for instance, dark matter decaying into neutrinos or even into leptons produce a lot fewer photons, and those usually evade this kind of bounds. But I will show you that in a moment. So this is something that we did a few months ago, actually, with a group of people. And here I'm showing you the case of dark matter decaying into BB bar, so soft channel, neutrinos peaking at lower energies. And then here I'm showing you dark matter decaying into W plus and W minus, a slightly harder channel. What is the good things about the annihilation, decays into quarks? In these plots I'm showing you the lifetime as a function of the dark matter mass. This is a fit to the 4-year HESI data, and this is the blue region is the allowed region. I think it's at 90% confidence level, or 95. Actually, I don't remember. No, it's not important. So what we see here is that the lifetime for a case of dark matter decaying into BB bar needs to be of the order of 10 to the 27 or so to explain the ice-cube data. And this is, as I mentioned before, this could be a problem. Those sort of lifetimes produce a lot of gamma rays, and there could be a problem with Fermilab data. The good thing about this kind of channels is that it comes in this plot. This plot will show you the normalization of the astrophysical flux. In this fit, I think I didn't mention, in this fit what we are doing is we assume there is a dark matter contribution in terms of coming from this dark matter decaying into these channels, plus an astrophysical contribution which we model as a power law flux. So and we leave free the normalization of the flux and the power law index. And basically those two parameters are shown here, the normalization of the flux and the power law index. And what we see here is the best fit for this channel on the astrophysical contribution is a relatively hard astrophysical spectrum. So a spectrum with an index very close to 2.2, 2.1. And why is that good? Well, I mentioned at the beginning, and also Juan Pablo yesterday mentioned that there might be a little bit of a tension between the HESI data, which prefers a slightly softer spectrum with e to the minus 2.9 or something like that, if evaluated in terms of a single power law, with the through-going sample, which prefers a much harder spectrum, which is e to the minus 2.1, 2.2, whatever. And this kind of contribution, this kind of model, dark matter plus astrophysical flux, prefers a higher spectrum, which would be in agreement with the through-going sample. So on that regard, this decay channel seems good. Doesn't seem so good from gamma ray data. Then when we go to a harder channel, what happens is that we get much longer lifetime. So this was 10 to the 27, a few times 10 to the 26. This is 10 to the 28 or even 10 to the 29. So much better. So longer lifetimes means fewer gamma rays, which is good. So no problem with that. On the contrary, this predicts a very, very soft astrophysical spectrum with an index of e to the minus 3.6 or something like that. This might be a bit complicated to explain, but one can think of the tail of an astrophysical contribution that would just be falling off, and that could be a good explanation for that. You see that, for instance, in the case of dark matter decaying into quarks, the black line here, the black histogram, is the dark matter contribution, and the green histogram is the astrophysical contribution. So you see that actually the green explains, the astrophysical contribution explains roughly the high energy events, and the dark matter decay explains the low energy events. On the hard channel, basically the dark matter decay explains the high energy events and is the astrophysical contribution that explains this lower 100 TeV or so events. Okay, so this is what happens with even harder channels. This is decays into muons, decays into neutrinos, very similar qualitatively to the case of dark matter decaying into gauge bosons. It's a hard channel, basically long lifetimes, no problem with gamma rays, and but the astrophysical spectrum is quite soft. Again, dark matter decays explains the high energy part of the spectrum, and the astrophysical part, which is the green, explains the low energy part of the spectrum. This makes it more difficult maybe to be in agreement with the through-going muons. Okay, and so we also consider, here we are considering dark matter decaying into a single channel. This is not realistic. Obviously, you would have for a particular model of you have a model with your dark matter particle in the PeV range, and that dark matter particle will decay in a combination of channels, and that is what you have to use. But just for reference, you can just show the results for a given channel. But in those previous analyses, I show you what are the results for dark matter decaying in a particular channel plus an astrophysical contribution with a power law flux. Now, we can also ask, can we actually explain the entire spectrum with a single dark matter contribution? And for that, can we just, for instance, consider 2 decay channels and see if we can actually fit the spectrum with only dark matter decay? And actually, the answer is yes. Here I'm showing you a couple of cases, but we consider a different combination of decay channels into soft, hard, with quarks and neutrinos, quarks and leptons, quarks and gauge bosons and neutrinos, all kind of, in the paper you can see those. But just as an illustration, here you see that actually you can explain very nicely the spectrum seen by IceCube in terms of only dark matter decay. What is the problem in this case is that you see that you need about 90% of branching ratio into quarks. And I mentioned before that decays, sorry, I keep on saying annihilation is all the time, it decays. So I said before that decays into quarks produce a lot of photons in order to explain the data. And it turns out that in order to explain the entire data with only dark matter decay, you need a huge branching ratio, 90% into quarks. So that might bring problems with gamma ray data. So, sure.
Yeah, your branching ratio is defined by the lifetime of the dark matter.
No, we fit both. We fit the branching ratio, we fit the lifetime. But it turns out the lifetime, the lifetime require actually it's here somewhere here. The lifetime required here is of the order of 10 to the 27. Yeah, that is here is 10 to the 27. Here is, yeah, it's the same actually. Very similar. Oh, yeah, it's very similar. So, but we fit both. I mean, we fit branching ratio and we fit the lifetime. And the lifetimes required for this are similar to the lifetimes required when we did the analysis of only dark matter plus astrophysical flux with soft channels. So it turns out that you produce very similar amount of photons in this case as in the previous case of dark matter only decaying into quarks plus astro.
Yeah,
So.
in this case, for example, apparently you solve the problem of the density of photons we produce because the lifetime is 10 to the...
But the lifetime is too short. It produces, the lifetime is similar to the lifetime we need when... It's still too short. I mean, it's not exactly the same as when we do the analysis of dark matter plus astro. The dark matter, the lifetime in that case for decays into quarks is slightly smaller. In this case, it's not that small, but it still is small enough for the gamma rays to peak in and having problems with that. And if the branching ratio was 90%, but it was 1%, that would be okay, obviously, with a lifetime of 10 to the 27. But it's 90%, it's very similar. So basically, in the end, the gamma ray limits you get in this case and in the other case are very, very similar. But anyway, from the purely neutrino point of view, this fits well the data. As well as 2 power law, as well as 1 power law plus 1 dark matter. So all of them are actually statistically the same. Within 2 sigma, all of them, there is no way to distinguish all these 3 cases, or actually 4 cases. There is no way to distinguish an astrophysical flux with a single power law from an astrophysical flux with 2 power laws, from an astrophysical flux with 1 power law plus dark matter decay, from dark matter decay with 2 channels. All of those cases are within 2 sigmas. Okay, and these are just some limits. We can take this problem and instead of saying, I'm going to try to explain the data in terms of this dark matter decay. So what I do is trying to take the data and see what is the maximum amount of dark matter contribution that I can have in the data and set limits on the lifetime of the dark matter particle as a function of the mass for different channels. And this is what we saw here. This plot here is for decays into quarks. This is for decays into gauge bosons. This is for decay into muons, and this is for decays into nuis, I think. And you see that, for instance, in decaying into quarks, these are the bounds that one gets with IceCube data. And this line here is the bound you get with gamma rays. So everything which is below is excluded. So you see that with gamma rays, this is the best fit we get, and this is the tension. So it's a tension within 1 and something sigma with gamma ray bounds. So the limits coming from gamma rays are much stronger than the limits coming from neutrino data. This is for decays into quarks. When you go to decays into gauge bosons or even decays into even harder channels like leptons or neutrinos, the limits for the limits on the dark matter lifetime coming from neutrino data are much stronger, but basically an order of magnitude stronger than gamma ray limits for masses above, say, 200 TeV. So in this case, neutrino data is much better than gamma ray data. Okay, and just flashing a little bit more on dark matter decay from the theory side. So there are different ways to produce, because all this was phenomenological. So when I say, okay, we are just putting a dark matter mass and we are putting a lifetime and seeing what is a particular channel and see what is phenomenologically what one would see. But actually, can we have a model with a PV dark matter that would produce this kind of neutrino events in IceCube? And actually, there are many models in the literature. This is just one model I wrote with Pasquale Di Bari, and a student, actually a postdoc. And basically, what we did here, very briefly, I don't want to bore you with the details of model building. We consider a solution where actually we could explain the matter-antimatter asymmetry of the universe and produce a dark matter candidate. Typically, in standard seesaw scenarios, the right-handed neutrinos that one adds, actually Adele discussed this in quite detail yesterday, are very heavy, but they decay very fast in order for leptogenesis to succeed. So none of them can be a good dark matter candidate. But one solution would be well, maybe we can just decouple one of the Yukawas, and basically that new right-handed neutrino would be completely stable. Well, that would be a solution. That would be a good dark matter candidate. But the problem with that is that in the first place, you need to produce it. So you don't have Yukawas, you don't produce it. So you can break this thing a little bit, and you can allow for a little bit of right-handed mixing between the right-handed sector via a Higgs portal-like interactions of this sort. You have Higgses, and these are right-handed neutrinos. Actually, this scenario was suggested by Anisimov and Divari way before IceCube had any data, like 8 years ago. And actually, you could, in this way, by allowing for non-diagonal Yukawas, one can produce these right-handed neutrinos, produce the asymmetry, dark matter and antimatter asymmetry, and having a good dark matter candidate which is not completely stable, and produces via non-thermal process, non-adiabatically, from, as I said, right-handed neutrino mixing. Well, actually, when one works out the details of the model, it turns out that there are some regions in the parameter space which would produce signals in IceCube. For instance, here is the lifetime as a function of the mass, and you see that we have to be around this region to have a good explanation of all these problems. Actually, this is the mass of the dark matter. Of the dark matter particle and another right-handed neutrino, and we have to be above this line in order for leptogenesis to work. And this region here corresponds to this region here. So it turns out that there are regions in the parameter space where the lifetime is of the order of 10 to the 28 seconds, and the mass of the dark matter candidate, one of these right-handed neutrinos, is in the PeV range. So it turns out that this model provides the explanation of the matter-antimatter symmetry, provides a dark matter candidate in the PeV range, which is the case with a lifetime of the order 10 to the 28, which is right what you need for dark matter for IceCube. Actually, you can see this is not a fit. This is just picking some parameters, some particular point in the parameter space which is allowed, and we explain all these problems, and just trying to see what is the expectation in the IceCube detector compared to the 4-year data. And actually, you see that it's quite reasonable. This is the dark matter contribution, the black line. The green is the astrophysical contribution. This is fixed at e⁻², which is what one would expect. And you see that it explains nicely the energy distribution. There are many other models in the literature. There are models with extended standard model with a U1B-L symmetry with free right-handed neutrino. Actually, this is very similar. This is by Higaki and Kitano and Sato. Actually, this is very similar to what we did. Actually, it's very similar to this Yukawa structure in Anisimov and Divari, just by decoupling this one of Yukawa, although the production, instead of being by non-adiabatic production in the early universe, this is via inflaton decay. Yeah, no, I don't want to get into the details. Anyway, you get very similar type of predictions in the terms of mass and lifetimes. There are other models in the literature, like PeV right-handed neutrino in a discrete model. This produces also resonant leptogenesis. Always, usually, basically, in all the cases, you need to produce these neutrinos, this dark matter, in a non-thermal way. There are signatures at colliders. Here there's another paper with a U1 dark age sector, and actually here predicts a slightly different signature in IceCube, which because in this model dark matter decays into 3 particles and that produces a softer neutrino spectrum. In all the cases I've been discussing so far, dark matter was decaying into 2 particles, and that produces a much harder spectrum. Here is 3 particles, so the spectrum is slightly different. But there are many different models in the literature. Actually, here they studied in a more generic way dimension 6 operators. They didn't consider dimension 5 operators just because that would produce very fast decays. So they went to dimension 6, and they consider actually in this context leptophilic dark matter to avoid, for instance, gamma ray limits. Remember, dark matter decay into quarks produce a lot of gamma rays. So here they consider only leptophilic dark matter, in which case dark matter couples to leptons only. And they consider different scenarios, and actually they did some kind of simple fits to the data, and to evaluate what is the regions in the parameter space of this generic type of interaction terms. And and many other. Here I show you just a list of that I won't discuss. But most of these are left-right models that all of them produce PeV dark matter with lifetimes in the right ballpark for IceCube to detect these kind of signatures. Okay, so let me move on. A lot of dark matter decay stuff. And let me say a few more things about dark matter, but in a completely different context. So this is what is called boosted dark matter. In this case, dark matter is composed of two particles. One is much heavier than the other, and one is not completely stable. The heaviest state is not completely stable and actually can decay into the lighter state. It turns out that when the heavy state decays into the lighter state is very boosted just because of the ratio of masses. And if we have a heavy state in the PeV range and the lightest one just much heavier, much lighter, it's not that important at this point. We have dark matter decaying into another dark matter particle very boosted. That dark matter particle which is stable flies from the production point to the detector and then hits the nucleus in the nuclei in the detector and produces some kind of signature. So this is represented in this diagram. You see this is chi interacting with the nucleus in the detector via some new mediator. You need a mediator for this particle to be coupled with the standard model, and that produces a kind of signature which is a neutral current-like signature. So that would modify, for instance, the energy spectrum that you would expect from an astrophysical flux, but would also modify the flavor composition. Neutral current are showers, so that would modify the flavor composition. Actually, these people who proposed this mechanism show that to explain, actually this mechanism was proposed to explain the PeV events again, and the ratio of the lifetime divided by the Kaplan square of this new interaction, dark matter nucleus, has to be of the order 10 to the 24 seconds, which is perfectly fine in this case, because dark matter here is decaying mostly into this new state, dark state, this second component of the dark matter of the universe. Actually, this was in the first paper, the suggestion of this model, but then there were three people, Kopp, Liu, and Wang, who realized that actually we have this model has a dark matter particle in the PeV range, another dark matter particle much lighter, but in order to connect with the standard model, you need some mediator. But if you have a mediator, you can have, as I mentioned before for dark matter decay, that you have always electroweak corrections, so electroweak Bremsstrahlung, you would have new sector Bremsstrahlung via this mediator. In the same way as you have W Bremsstrahlung or Z Bremsstrahlung in the case of the standard model, here you have a new mediator that can also produce Bremsstrahlung. And when this Bremsstrahlung is produced, this new mediator would decay into standard model particles, because that mediator is the one that connects dark matter sector with the standard model sector, so it would decay into standard model particles, and would also produce low energy events in IceCube. So in principle, there might be no need of astrophysical neutrinos also to explain this within this scenario. You can explain all the events in IceCube with this boosted dark matter cases. And actually, they pointed out that maybe they could even explain the galactic center gamma ray excess in the 30 GeV, 40 GeV regime with this lightest state. This was done for a pseudoscalar case, and then the people who did the first paper considered different cases, different mediators, scalar mediator, vector mediator, pseudoscalar mediator, and they did the analysis of what each of these cases could do in the data. And in some cases, actually, this is the orange histogram is the astrophysical contribution. So in some cases, you see that you needed an astrophysical contribution, then you have the Bremsstrahlung, which is the blue, and this greenish region, which is the contribution directly from the boosted dark matter interaction. So in some cases, like scalar mediator, you need astrophysical neutrinos, or for instance, the pseudoscalar case, basically you only explain the low energy events in the tens of TeV range with this kind of model. But for instance, light vector mediator doesn't need to have any flux of astrophysical neutrinos to explain the data. Anyway, this is just a collection of exotic cases that might or might not, or could not explain the data, but they could be at least bounded. Okay, more about dark matter, but here is not decay, is not interaction directly in the detector. It has to do with propagation. So what if dark matter and neutrinos interact? If dark matter and neutrinos interact, then the neutrinos coming from the galaxy, actually not, they don't need to come from the galaxy, but they have to go through the galaxy, would interact with dark matter in the galaxy, and that would produce basically an absorption of the flux of neutrinos coming from that direction. So if the dark matter neutrino interactions were strong enough, we might expect to see kind of a different angular distribution. So we expect to see a deficit of neutrinos coming from the direction of the galactic plane. And actually this is what is shown here. This is the data in gray, and the black is what you expect for an astrophysical isotropic distribution. And if you have other interaction, this zero here is the point pointed towards the galactic center. So you see that we expect much smaller number of events coming from the galactic center direction. So basically, and you can also even suppress the energy spectrum, producing dips in the spectrum. So by doing this, you can set bounds on different type of interaction, like a scalar dark matter, fermion mediator, fermion dark matter, vector mediator, different classes, and you can constrain the parameter space, which is like the mass of the mediator, the mass of the dark matter, and in color is the coupling of this kind of interaction. I don't want to get into the details, just to show you that that IceCube can be complementary to other type of searches, like cosmological searches, like for instance using this type of interactions using the observation of large scale structure to constrain this, because this would produce collisional damping and would modify the shape of the power spectrum of matter. So anyway, this is just to show that IceCube is complementary on searching for dark matter neutrino interactions. So what about flavor? Here so far, how long?
5 minutes.
5 minutes? Okay. So I have 5 minutes. Good. So here I've been discussing about energy distributions, angular distribution, but there is another observable, which is flavor. And flavor carries information about the mechanism of production, but it also carries information about the way neutrinos propagate from the source to the detector. And actually we can search for exotic physics by searching for different flavor compositions at the source. And just in short, already Juan Pablo mentioned this, we have some flavor composition at the source, and what we see is some flavor composition, or what they try to do in the detector is trying to see from the cascades and the tracks, trying to infer what is the flavor composition at the detector, and from that we try to infer what is the flavor composition at the source to see if everything is compatible with what we expect with standard physics, or we need some new stuff. And we know that these distances are very long, so basically neutrinos reach the detector in a coherent mixture of mice eigenstates, just neutrino oscillations get completely averaged out, and basically it's a product of probabilities, and one can compute that. Actually, you see, Juan Pablo already mentioned these different standard cases that are usually mentioned on production, so pion sources or different type of sources. And just I'd like to stress a couple of things in this kind of these numbers. So this is the flavor composition. These are the flavor composition at the source. So if you produce neutrinos via pions, you produce basically 1 electron neutrino and 2 muon neutrinos. And here neutrino means neutrino or antineutrino, because the detector cannot distinguish. So I'm just putting them together. So you produce 1 electron neutrino and 2 muon neutrinos. After neutrinos propagate these astrophysical distances, basically you get equal flavor composition at the detector. And you can play with all the different cases. And the important thing is that this is a standard physics, just pure neutrino oscillations. And you see two features which are here, which no matter what you put here will always appear. So what you see here? That no matter what is the composition at the source, and there are quite extreme cases. Here you see even 100, which is neutron decay, or 010, very extreme cases. No matter what you have here, you always have all flavors populated at the detector. So this is one feature which is important to have in mind. And the other one is that you see that no matter what is the flavor composition at the sources, the composition, the fraction of nu mu and nu tau is approximately always the same at the detector. And this has to do because this has to do with maximal theta 2-3. The fact that theta 2-3 is very close to 45 degrees means that no matter what is the combination here, you always get the same amount of muons and taus neutrinos at the detector. Okay, so this is just one of the flavor triangles. And actually, we in a couple of works were the first to do this kind of analysis using ice cube data. And basically, what we see here is just pure nu E. This is the vertex here, just to explain you a little bit what is this flavor triangle. Pure nu E. This is pure nu mu, and this is pure nu tau. And the farther you are from that vertex, the less contribution in that flavor. And basically, you can just get, for instance, this point here. You want to know how much nu E flavor you have. Basically, you draw the parallel to the opposite side to this point. You go, it crosses here, it's like 0.05 or whatever. You do the same for the others, and you can get what is the flavor composition in each flavor. This region here are what is the expectation of the flavor composition at Earth, no matter what the flavor composition at the sources are. Here we are varying all possible composition at the sources and just letting them propagate and taking into account neutrino oscillation. Actually, the width of these regions have to do with the uncertainties in the neutrino mixing parameters. If we just fix the neutrino parameters, this is just a very thin region. And these two regions, just in case someone asks, has to do with the results of the fits for different hierarchies. Anyway, so whatever flavor composition you have at the source, you always have to lie here after neutrinos propagate. So if in the ice cube analysis, you get a point which is outside this region, no matter what you do, new physics is required. So this is why flavor studies are so important. That doesn't mean they are easy. They are very difficult, and actually to constrain this at the level enough to actually say that we are seeing what we should see in flavor composition or not is a very non-trivial task. But this is what happens. Any point outside this region means new physics, and this is if and only if. Okay, some very fast thing. For instance, neutrino decay. We know that neutrino decays in the standard model are very weak. Say that the neutrinos live for a very long time. You see. This is of the order of 10 to the minus 47 seconds, the width of the decay. In three neutrinos, relative decay is of the same order. So this is, we couldn't expect to see any neutrino decay with the standard model physics. So if we detect neutrino decay, that means that we need new physics. We need new particles coming into play in order for neutrino decay to happen at the rates that are observable. So this was, for instance, suggested by these people, where they consider scalar coupling with a pseudo-majoron. Basically, with neutrino decays, with neutrino telescopes, one can prove ratio of lifetime versus the mass of the neutrino of the order of 10 to the 3 seconds per electron volt. And actually, you don't see this, but basically, these two lines here, this is atmospheric neutrinos, these are solars, and these are ice cube neutrinos. So actually you can reach several orders of magnitude better sensitivity with astrophysical neutrinos on this quantity. Well, and as I don't have much time, I won't get into the details, but basically what the neutrino decay does is modifies the flavor composition at the source, for instance, at the detector. For instance, if all neutrinos decay into the lightest neutrino, actually no matter what the flavor composition at the source is, what you get at the detector is only nu 1, the lightest one. So basically the flavor composition is UE1, where U is the mixing matrix, the neutrino mixing matrix is UE1 square, U mu 1 square, and U tau 1 square, and that is here, which is very far from the plot I showed you before. And actually, in this way, these people here concluded that complete decay of nu 2 and nu 3 into nu 1 is this favor within 2 sigma, around 2 sigma in ice cube. And well, you can do this also with pseudo-Dirac neutrinos, and I don't have time for this, but basically you can have any incoherent mixture of mass against state with different mechanisms, and you can play with all incoherent mixture of mass against state and see what you can get, and different type of models would give you different combinations. And this is the region you would cover at the detection, not even the full triangle. So actually covering the full detection, the triangle at detection is very, very hard. And actually, as I said, full incoherent mixture of eigenstates in all possible ways doesn't really cover. You need even more extreme scenarios. You need like a scenario where you actually change the propagation completely. For instance, scenarios like Lorentz violation or violation of the equivalence principle, where all the physics come from the flavor structure of the new sector. And actually, this is the plot Juan Pablo showed yesterday. This is what we expect from the standard scenario. And actually, these kind of operators are constrained in different ways with different type of experiments. And these are the current constraints. And this is what is the allowed parameter space so far with the current constraints coming from different experiments. So actually, already IceCube can do much better than what is known, because this covers the full triangle, and we know that already the full triangle is not allowed. So this can be also used for these very exotic, to bound these very exotic scenarios. This is some other gravity model that I won't have time, leptoquarks that basically modify the event spectrum at the highest energy. Again, this is just quarks coupled with two leptons via this new particle, which is called a leptoquark, which has to have a mass of the TeV range. Number of works in the literature. But anyway, so there are many other scenarios. I would need like 3 lectures for this. Coherent neutrino dark matter interactions, shortcuts in the X-ray dimension, the case of hundreds of PeV particles, secret neutrino interaction with MEV mediators, non-standard interaction. Maybe you have some proposal at the company here. Anyway, let me conclude. So in addition to the to be produced by standard mechanism like AGNs, gamma ray bursts, starburst galaxies or so, high energy neutrinos may be produced by other exotic sources. So we can try to constrain those kind of sources and the physics that those implies. And there are different physics beyond the standard model that can produce actually features in the spectrum that so far are not seen. Those features can appear in the energy and the angular spectrum and the flavor composition. So we can use them to at least bound all these new physics and all these crazy models. Thank you.
So we have time for questions.
So you discussed this. You mentioned here in your conclusions that high energy neutrinos could be produced by exotic sources, and you showed that some of the models could explain the data in the electromagnetic observed deposited energy.
Mm-hmm.
Is there a way to tell them apart from the standard explanation that they're just neutrinos produced by standard mechanisms from very high energy accelerators?
If there is a way.
Yeah, because it kind of looks like, after the measurement, then the model fits now the measurement, but is there a prediction that the model can make that would distinguish the two?
Well, there are ways, yes. There are ways with IceCube data only, or neutrino data in general, but also with gamma rays, as I mentioned. For instance, there are cases in which the data can be explained, or the particular model can explain nicely the data, the IceCube data, but it might be in complete contradiction with gamma ray data. It's difficult really to obey the gamma ray limits. They are very solid. So that is one way, but also within the very same IceCube data, you can do it. Right now, the problem is that we cannot say anything basically at any significant level. But in the future, the dark matter, for instance, dark matter signal has a distinctive angular distribution from the astrophysical signal. So that is one way.
Do you have that? I just probably I missed that. Like I only saw mostly energy distribution.
Right now, everything is good.
Yeah.
So.
No, but it's good to know which kind of.
So these are a bunch of analysis on the angular distribution of the data. And this is, for instance, this is the TS distribution of, in the case of dark matter decay. This is the TS distribution in the case of isotropic flux. And I think the p-value for this is 18%. This is 40%. So.
And when you do the dark matter decay, it's essentially given by the
this is dark matter
distribution
decay.
of dark matter in the galaxy.
Yeah, because that is the dominant one.
Okay.
And if the dominant was the extragalactic, there would be no way to distinguish that. Actually, I haven't saying continuously annihilation. I always meant decay, but I never discussed annihilation. Why I didn't discuss annihilation? Because in the case of annihilation, the contribution from the galaxy is rho squared. It goes with the square of the density, and then the contribution from this could be much larger than this. This is actually uncertain, it's not completely clear, but what we know so far, the contribution from the extragalactic dark matter annihilations would be smaller. But on top of this is not only larger, but also is more peaked, because dark matter is peaked towards the center. If you put a Rho square, it's more peaked towards the center. So the angular distribution of dark matter annihilation is more different than dark matter decay, and that is difficult to accommodate the data with that. But yeah, angular distribution, gamma rays, there are different ways to do it. It's not easy.
Thank you.
So in all those examples that you showed for dark matter or for neutrino decay, I mean, in the way that you show it, it's that you are using one of these three features, right? The energy spectrum, the angular distribution.
Basically, there is no other feature.
No, but you could combine in the analysis to.
Oh yeah, no.
And
And in some of the cases, I mean, I didn't get into all the details, and I was stressing the dominant feature. But in some of the analysis that I saw, in some of the plots that I saw, also, for instance, angular. I mean, for instance, actually in our analysis, here in our analysis, this kind of plots, we include all. We include energy, angular, and topology. So all that information is included in the analysis. So there are some analyses which are more simplified and only take one into account. Also, that only care about one particular case, but in principle, you should treat everything into account.
Yeah, I assume it, but yes.
Yeah.
So my question is, in principle, you could also have two different dark sectors that are unconnected. One of them decay, and the other one is stable in such a way that you basically relax the lifetime, right? That
Yes,
mean
but
you will have the relic
you mean
density,
you
mainly the relic density.
you realize the
coming from-
lifetime in which sense? Because the lifetime is what tells you how many events you see in ice cube.
Yeah.
The point is that yes, that you are thinking about this in the way of relaxing the gamma ray bonds. Yeah, but if you suppress, if you increase the lifetime,
Kill the events.
you don't have problems with gamma rays, but you don't see events. So the point is that they are both linked.
More questions? The students? Come on. No? Let's thank Sergio.
What dark matter candidate is the favorite for PAVs?
Sorry,
What dark matter candidate is the favorite or
favorite?
for PEVs?
Favorite, I have my paper. So, but it's not. There are many candidates. We have this candidate with a right-handed neutrino mix in the right-handed sector, and you produce this non-adiabatically. You have all these kind of models with different right-handed neutrinos produced via inflaton decays, that produce in a non-thermal way, that have signatures in colliders. There are these cases that I'm probably missing some models. I'm just sketching some. There is no favorite. This basically, all I wanted to say with this kind of 3 slides or so, showing like 8 or 9 models, is that showing that actually getting a model with PeV dark matter is not completely so crazy. So you can get dark matter in the PeV range that actually is not only a dark matter candidate, but explains other problems. Like for instance, it can give you a successful leptogenesis. So it's not a matter of what is better or worse or what is more favorite. There is not really a favorite one. It's just a proof of concept. Like actually, you can have that kind of candidate to explain ice cube events.
One more? If not, let's thank Sergio. And we move to the talk by Juan. And he will talk about what can we learn from diffuse supernova neutrino background.
Sí.
Yo creo que sí. Okay, so hello everybody. I would like to thank first to Miriam Mondragon and the organizers for inviting me to be here. It is always a pleasure to be at UNAM. So what I want to talk with you is something that is very easy. It's the diffuse supernova neutrino background, and some things that we can learn from this flux. So essentially there are three things that I want to talk with you. So first I want to tell you what is this diffuse supernova neutrino background. The second part is if this diffuse supernova neutrino background can tell you something about cosmology, and I will try to conclude with something. Okay, thank you. So essentially what we have is, we know that supernova exists. So in 1987 there was a surprise for everybody. There are some of us that are waiting that at the morning we are going to open the eyes and we will see a star in the sky that will be a supernova. Especially, it will be great if there is a galactic supernova, but in 1987 there was a supernova just nearby in the Nubes de Magallanes. There was a huge explosion on February. So it was, this was, so where is the point? This one. So there was this star. So this was one day, 22 of February, 23, this was the same place. So a supernova exploded. And actually, from this supernova, there was the first observation of extragalactic neutrinos. There were something like 19 events. From these 19 events, there were like 1,000 papers discussed in physics about this. Actually, it will be a dream if we have a. I think. It doesn't matter. Well, in any case, so we have these observations. It was actually an accident that these detectors were working, and then they saw some neutrinos, 19 neutrinos. So essentially, these neutrinos they come from the death of a star. So you need a very massive star, so something like more than 8 solar masses star. So the star is going to end. It's going to finish its fuel. So once the fuel is over, gravity starts to win, and then essentially all the matter wants to go to the center of the star. So in order to proceed to this squishing of the star, imagine you have some electrons and protons. So the electrons are going to be squished to the proton, and then the proton is going to have a inverse beta decay, and then it is going to produce a neutron and emit a neutrino. So the only possible way in order to squeeze the star is you have to produce a lot of neutrinos. Actually, 99% of the energy, of the gravitational energy released in a supernova explosion is liberated in form of neutrinos. So forget about gravitational waves. Most of the energy goes out in form of neutrinos. And these neutrinos, so essentially, all the matter is falling down. It reaches the center of the star, the matter, and then at this moment there is a collision of this matter, and then it goes the luminous explosion of the star, and then is the light emission of the supernova. So essentially, you are expecting some neutrinos that should arrive before the explosion of the luminous signal of the supernova. And actually, the people is expecting that some supernova should explode soon in our galaxy, and in principle, neutrino detectors will observe these bursts of neutrinos, and after these bursts of neutrinos, they are going to tell to the observatories, be ready because there will be some flash in the sky originated from this collapse of the supernova. So it is not the end of the star, because actually after the explosion of the star, all the material is is expanding, and actually the remnants of the supernova probably is the source of the ultra high energy neutrino cosmic rays. So, yeah, okay, gracias. So actually supernovas are very exciting. So we can just wait until the next supernova explodes, or what you can do is to take, imagine along the history of all the universe, there has been a lot of supernovas that have exploded. So just take all the neutrinos that have been born from all the supernovas in the universe along all the history of the universe, and then sum all of the neutrinos, and what you will arrive is a diffuse neutrino supernova background. So in principle, there is something like 10 to the minus 11 neutrinos in 1 centimeter cubic of this supernova. It is an isotropic flux with some distribution of energy. So what we know from the flux of neutrinos is that it covers a huge range of energy from very low energy. So usually from these diffuse supernova neutrinos is called relic cosmological neutrinos, which sometimes are confused with the ones that are produced from nucleosynthesis. So what we are not interested in these ones from very low neutrinos, so we are interested from the ones produced by supernova. So these are the flux produced by the 1987 supernova. If you sum all the supernovas around the universe, along the history of the universe, you will finish some flux which is extremely small compared to the one produced by a galactic or a nearby supernova. So this is the flux we are interested in. This is isotropic, constant in time flux of neutrinos permeating all the universe. It is very easy to compute, even that I can compute. So essentially it has 3 ingredients. What you need is the Corcola supernova rate. So essentially how many supernovas explodes in a galaxy or in the universe. So you need to know how many supernovas are exploding as a function of the time of the universe, or equivalent to the redshift of the galaxies. You need to know what is the amount of neutrinos that each supernova exists, and essentially you have to sum all of these neutrinos, so you have to do the integral over the cosmic time. But the cosmic time is related to the Hubble parameter, so essentially you need 3 ingredients. How many supernovas, what is the number of neutrinos that each supernova emits, and what is the expansion of the universe, because if the universe is expanding very fast, so it doesn't matter that it produces neutrinos, the neutrinos will never reach us. So essentially it has information about the expansion of the universe. So let me go a little bit on the details of each of the ingredients. So essentially, in order to compute how many supernovas you have, you need to know how many stars you have. And from these stars, how many of them are bigger than 8 solar masses that are most probably going to collapse in a supernova. So essentially, you even can have some observation about, you can look for a galaxy, put your telescope, and then start to count how many stars are there, and then from that you can infer what is the number of stars that you can see as a function of the redshift, and then you can know what is the star formation rate of supernovas observationally. Of course, these points depends of how do you measure the distance in the universe. So you have to know what is the expansion of the universe in order to put points in this plot. So essentially, this flux depends on the cosmological model that you are using. So, but in any case, the current knowledge about the Corcola supernova rate is a combination of this observation, of direct observation of how many supernovas are exploding in each galaxy, about how many stars are at different redshifts, and actually these measurements can be compared with some model of the universe. So you take your favorite cosmological model. So for instance, take the lambda CDN model, and then what you have to do is start with your density perturbations, linear density perturbations originated from some initial spectrum of inhomogeneities, and then evolve the universe, and then from this evolution of the universe you can see how many galaxies are going to form, and then under some assumptions you will get how many stars you are expecting that they can form. So actually people are doing that, and everything within a lambda CDN model, everything is consistent. So you can have the observation and you can have the prediction, and essentially except a factor 2 perhaps, there are concordance on the knowledge about what is the Corcola supernova rate as a function of the redshift. So this ingredient is more or less clean. Of course, you will have some dispersion on the data and on the predictions from structure formation, but it is a reasonable error bar. This star formation rate can be parameterized in this way, where these coefficients can be fed to the data. So what about the neutrino energy spectrum? So how many neutrinos each supernova produce? In order to know what is the number of neutrinos, what you have to do is essentially to simulate the supernovas. And there has been a huge improvement on the evolution of the Corcola supernova simulations, where you can, by different equation of states, different models of neutrino transport, and so on, they have a more or less consistent way of producing Corcola supernova rates in simulations. From this, each simulation, they run different simulations. From those simulations, they compute what is the number of neutrinos as a function of the energy are produced, and then they realize that there is a general power law. Well, there is a general spectrum from all the simulations where these parameters are fitted according to the average of all the simulations that they have done. So essentially, this flux is known, which error, of course, that depends on the number of evaluations on the equation of state that you are using. But in general, we can say that we know what is the number of neutrinos that each supernova produce, and what is the spectrum. And the last part is the expansion. When you do the integral over the time, what you need to know is what is the Hubble parameter, which is essentially you can determine from the background solution to the cosmological model. So in instance, from a lambda CDN model, what you have is essentially that you introduce a cosmological constant plus matter that has effective pressure equal to 0, and then you solve the Freeman equation, and you get what is the Hubble parameter, and then essentially you have all the ingredients, and you have to do a very simple integral. So essentially what you have is what is the spectrum, the flux of neutrinos coming from all the supernovas as a function of the energy, and here this envelope comes from the uncertainties that you have from the Corcola supernova rate. So essentially, it's a very simple way of computing what is the diffuse superneutrino background flux. The good news about this flux is that its detection will be inevitable. So in the near future, megaton detectors like Super Kamiokande, so the probably Hyper Kamiokande or another kind of bigger detectors will detect the diffuse supernova neutrino soon. Actually, there is a proposal to include in Super Kamiokande to dope the water with the gadolinium in order to increase the neutrino capture on protons to produce inverse beta decay, and then actually you will have a cleaner way of detecting the antineutrinos coming from all this neutrino supernova flux. And actually, for an experiment like Super Kamiokande, essentially dotted with gadolinium, this is the number of events that we are expecting per year, which is not very far from the limit imposed by Super Kamiokande, because currently Super Kamiokande has looked for this diffuse supernova neutrino flux, and it has a limit that this limit should be lower than 2.9 neutrinos per second per centimeter square. For energy, for a cut of 16 to the right, because Super Kamiokande is sensitive to high energy neutrinos. Well, high, not so high as Q, but high for us. Okay, what can we learn from this? The diffuse supernova neutrino is going to be inevitable detection. So this is a very simple mechanism of. So in contrary to the other astrophysical neutrinos that we can have, diffuse supernova neutrino is a very clean flux. We know in a reasonable way how many neutrinos you are expecting. So it's not like the high spectrum of neutrinos like we saw in the previous talk, where we don't know if these neutrinos are produced from dark matter or from astrophysical source. No, in this case we know all the ingredients for this flux and should be there. Actually, so there has been some work on the diffuse flux in order to see if we can say something about, for instance, for the neutrino lifetime. So imagine that the neutrino decays. Since we are imagining that the neutrinos are traveling across the universe for very long times, along all the history of the universe, if the neutrino flux that you detect is lower than the one that you're expecting, it's possible that it is because the neutrino decay in this cosmological distance. So actually the limits that you can get from this for the decay lifetime of these neutrinos is the highest. So as Sergio said before, the cosmological neutrinos the astrophysical neutrinos are the best source in order to look for the neutrino lifetime. And you can do this exercise not only for active neutrinos, well, for active neutrinos decaying to active neutrinos plus something. You can this plus something can be sterile neutrinos. So you can play a lot of about the neutrino lifetime. But you can also learn some information about the supernova physics. So for instance, as we said, the neutrino spectrum, this comes from simulation of Corcola supernova explosions. And it has some free parameters. So imagine that you are able to detect the diffuse supernova neutrino background, and actually by using the limit that Super Kamiokande has not observed still the diffuse supernova neutrino background, you can have some information about one of these, some of the parameters of the flux. So actually what you know is that the temperature, the average temperature of the neutrinos that are emitted supernova should be in this region. And this is with the no observation of the diffuse supernova neutrino. And of course you can look for new physics, but one of the authors of this paper is in the room, so I think that they can ask to him. But essentially is, imagine that the neutrino interacts with some extra particle, in this case a scalar particle, and then what it's going to produce is that the flux will have some dips because there could be some resonance in the interaction of the neutrino with this extra scalar, and then the resonance will produce a suppression on the flux. So there are opportunities for looking for physics, standard physics or new physics by studying the diffuse supernova neutrino background. But what about cosmology? Actually, most of the flux come from low redshifts. So essentially, when you compute the diffuse supernova neutrino background, so you can say, well, I don't know what is the integration, so what is the value of set that I have to the zeta I have to put in order to compute the complete flux. But what you realize is that most of the integral, the contribution comes from low redshift. So essentially, the diffuse supernova neutrino background is sensitive to low redshifts. So if it is going to tell you something about the expansion history of the universe, it's going to tell you something about the local expansion of the universe. And for instance, in this case, we have the predictions for the number of events that you are expecting as a function of the Hubble constants. And as you know, there are some controversy between the values of the H0 predicted, well, fitted by Planck or fitted by the local measurements. So in principle, if you have a very high determination, a very precise determination of what is the number of events, you can see that the number of events is sensitive to what is the value of the Hubble parameter. But you will need that, what you see is that the major uncertainty in the prediction of the number of events comes from the fact that you don't know the Corcola supernova rate. So we're asking to our cosmologist friends that if they can have a clean prediction of the star formation rate from cosmological models, then these error bars are going to be reduced, and then actually we can start to thinking that the eventual discovery of the diffuse supernova neutrino background can tell us something about the local expansion of the universe. Actually, just by playing with this flux, as we already said, supercamionicandi has some limit on the diffuse supernova neutrino, and then if you let as a free parameter the Hubble parameter and the dark matter content of the universe, and then you compute what is the number of events that supercamionicandi should have been observed as a function of H0 and the dark matter content of the universe. So essentially what you see is that since supercamionicandi has not observed any antineutrino coming from this diffuse supernova, then what you are saying is that the value of H0 should be bigger than this line as a function of the dark matter content. So essentially, because of the non-observation of the diffuse supernova neutrino background by supercamionicandi, what we can say is that the local universe should be expanded faster than 25 kilometers per second per megaparsec. Of course, this is far beyond the precision that we have already from other things, but it is just we are playing with this thing. But once we are starting to think about this diffuse supernova neutrino background as a test for cosmological model, we can think if we can, what happens if you plug different cosmological models in the prediction of the diffuse supernova neutrino background. First, one may ask, why do you bother to model different cosmological models if we already know that lambda CDM is a good model for the universe? And there are some possible motivations of why we want to do it. And one is, for instance, if we try to imagine that the cosmological constant, for instance, arise from the vacuum energy, then if you compute in a naive way what is the expectation value of the vacuum, it is 120 a 10 to the 120 orders of magnitude, 120 order of magnitude difference between the value that you are observing and the one that you are predicting from the idea that the vacuum should be contributing to the expansion of the universe. So this is a problem. We need to understand why there is such a huge difference. One solution could be just simply because we don't know how to compute what is the vacuum contribution. So, or the other possibility is just the vacuum is not contributing. But in any case, if the vacuum is not contributing, why this lambda is so small? And the other problem is it is called the cosmic coincidence problems, and it is the problem that at this particular moment of the history of the universe, both the cosmological constant density and the dark matter density are of the same order. So people are trying to solve these two problems, and they are proposing that in the market there is a huge number of proposals. So for instance, one of these is called the logotropic universe, or the other is, for instance, a bull viscous matter dominated universe. And the idea of this model is essentially you don't have a cosmological constant. Essentially what you have is a dark matter dominated universe, so all the dark part of the universe is dark matter. And in the case of the logotropic universe, what you have is that the dark matter has a very particular equation of state given by this, and when you compute what is the Hubble parameter, essentially it has the same behavior as a lambda CDM, because there will be an effective contribution due to the pressure of the dark matter that contributes to the expansion of the universe. So in the case of the logotropic, you will not have any problem of coincidence, because you have only dark matter, and you are expecting that the density energy should be of the same order. In the case of a bull viscous matter dominated universe, it's the same idea. You imagine that the dark matter, the only dark component of the universe is dark matter, and this dark matter has some viscosity. And because of this viscosity, there are some places in the universe where the equilibrium is not restored, and because this non-equilibrium due to the viscosity is not reached, then there will be some effective pressure that behaves as a negative pressure that contributes to the expansion of the universe. But when you compute, when you are imagining some dark fluid with these characteristics, you should say something about what is this viscous parameter. In this case, we adopt that this viscous parameter is given by some parametric function of the Hubble parameter. But in the case of for people who is doing particle physics, you can actually from particle physics try to predict what will be the viscous coefficient that you will have if you have some dark matter component with some very interesting or complicated interactions among the dark matter in the dark sector. So the viscosity could arise as an interaction of the dark sector. But this is not the case that we are going to do. We are going just to consider that the viscosity is given by this parametric form. In the case of the bull viscosity, you can rewrite the Friedman equation in this way, and then you will obtain this Hubble parameter, where you have only two free parameters. In this case, these two free parameters essentially are the coefficients of viscosity that you have introduced in this effective viscosity. It is interesting that if you take the supernova data from the luminosity of the supernovas, you can just compute what is the luminous distance, and then make a fit, simple chi-square fit, and then in the case of the lambda CDM, you obtain the standard values of the dark matter content and the Hubble parameter at the present time of 70 kilometers per second per megaparsec, with a good goodness of fit. But if you repeat the exercise for the logotropic or the bull viscous dark matter dominator universe, the volumetric fluid, you will obtain again some different values for the value of Hubble parameter, and then you can have some fit for the parameters, but the goodness of fit is very similar. So under this ground, what we are saying is that essentially, if you have all information about the expansion of the universe using supernovas, all of these three models are similar. But what about, so this is the fit in the case. So what about this is the fit, so essentially the value of H0 as a function of the amount of dark matter and the free parameter of the logotropic, or in the case of the bull viscous fluid, this is the fit. So take, for instance, this characteristic dark matter models and compute what will be the number of events that we will detect in a detector like Super-Kamiokande enhanced with gadolinium, and indicate, and this is the plot that we get. So essentially, this line is the red line consists of the model that we call the logotropic. The dots are lambda CDM. So essentially, what we are saying here is that there is no distinction between a logotropic and a lambda CDM universe by using the diffuse supernova neutrino background. But it is interesting that if you take the parameters of the bull viscous matter dominated universe, the number of events that you will detect is much bigger than the one that is predicted by the lambda CDM. So essentially, you are saying, this is interesting. So what is happening? It is just saying that at local distances, the expansion of the history looks a little bit different from the one from the information that you can get from the supernovas. Actually, since you are getting a very big number of events for this model, you can ask, well, what happens if I now consider what is the Super-Kamiokande limit on the diffuse supernova neutrino flux, and essentially, if you contrast what is the value, the values of the free parameters for the viscous dark matter universe, dominated universe, this is the fit that you get from supernovas. If you overimpose what is the values allowed in order to not have so many events that should be according to the Super-Kamiokande limit, so essentially you exclude all this region. So essentially what we are saying here is that already the limit imposed by Super-Kamiokande can help us to constrain in a more effective way cosmological models. But of course, we may conclude this, that diffuse supernova neutrino background is sensitive to the cosmological model, but we have to be very honest in the sense that when you compute this thing, so essentially what we are changing is this part of the flux, but we are letting the corporal supernova rate as the one that is in concordance with lambda CDM. So essentially, the flow diagram that you are following here is, imagine that you have a cosmological model. Then, because you are a theoretician, so you say, okay, I have a cosmological model. So the first thing I have to do is to fit supernovas in order to see if it is a reasonable model. So it does. Very well. The next step is I have to see if it produces the linear perturbation theory correctly. It does. Imagine that this model, it does. And actually, you are able to produce what is the large-scale structure of this model, and it is very similar to lambda CDM. So the conclusion is that most probably the star formation rate will be very similar. Imagine that scenario, that essentially this alternative cosmological model produce a very similar star formation rate as lambda CDM. How can you distinguish which model is the good one? Compute the diffuse supernova neutrino background and see if there are some difference, appreciable difference in this, in the prediction of events. That will be the dream. Well, of course, it is very. The star formation rate has been done only for simulations from lambda CDM. Of course, if you need a trustable star formation rate when you change the cosmological model, and this is something hard to do, but should be it's something that people should be starting to look forward, because the star formation rate, as we already say, is there. So actually, if you want to test a cosmological model, start to think in compute what is the star formation rate, because you can compare with data. So it is another alternative way of testing cosmological models. Well, so essentially the conclusion is diffuse supernova neutrino background is going to be detected soon, as long as megaton detectors will be available. So if I understood correctly, essentially the idea of this meeting is to discuss what things we can do, right? So I don't know, but something that has getting everyday attention is that there is a possibility that dark matter can be modeled by ultra-like scalar field, ultra-like boson. The model is very simple. Essentially, what you have is general relativity plus a scalar field minimal coupled to gravity, which has just the normal kinetic term plus some potential. You can imagine the simplest potential for this model, which is the mass of the scalar field. So you have m squared phi squared. So you have only one free parameter for this dark matter model, plus a cosmological constant. Well, you cannot have anything with only one parameter. But anyway, this model is very nice in the sense that you have only one free parameter, the scalar field mass. It is interesting that if you consider a scalar field with some mass of 10 to the minus 22 electron volts, the Broglie length wave of this particle will be of the size of kiloparsec. So it is of cosmological interest. Actually, people has worked with this idea from long time ago, from 2000 to now. And the idea is very simple. So you start with inflation, something happens that produces ultra-light bosons because it has a very high temperature. There will be a Bose-Einstein condensate formation from this ultralight boson. It is interesting that in the case of an ultralight boson, the Bose-Einstein condensation is a high temperature phenomena. So the boson produces a condensate. Then you go through the radiator dominated phase of the universe, and the scalar field behaves exactly as a radiation. But as long as you increase the evolution of the time, there will be a time in the universe where this ultralight bosons behaves as dust. So essentially, you will have that this very simple model for a very small mass of the scalar field behaves exactly as a cold dark matter. Of course, there are many questions because I am talking about a classical field, but then I am talking about a Bose-Einstein condensate. So we don't know how this transition occurs between the quantum and classical, but this is a problem, fundamental problem in physics. So the second part is you have after you have that the scalar field behaves as dust. As we already said, you have to compute what are the linear perturbations, and it is interesting that when you compute the linear perturbations, there is a cut in the power spectrum. And this cut in the power spectrum can solve some problems at small, well, not small, but galactic scales. So the question is this cut already observed or not with the data? But once you have this linear perturbation, then you have to the nonlinear regime where you have the structure formation, and then you have to study how you go from linear to nonlinear. So you have to do evolutions, numerical codes or whatever. And then when you have the structure formation, it is interesting that then you will have some objects like boson stars, very big self-rotating objects made of scalar fields. And this galactic, at this galactic level, this self-rotating objects has not a problem for the core cusp problem at the center of the galaxy. So this is a very simple model. It is getting interest after Oestreicher, Tremaine, Witten, and Hugh already saw the potentiality of this model. So now people is getting involved in this model. The model now is called fuzzy dark matter or ultralight action dark matter. Action, I think it is a little bit misleading, but in any case it is called in that way. But something that it is interesting from this point is that essentially the flux that you produce in some source, if it interacts with the medium, it is going to be suppressed. And the suppression will be just depends on the cross section. So in the case of a particle that has a very small mass, something like 10 to the minus 23, 10 to the minus 22 electron volts, you will have a huge suppression on the flux, even if the cross section is extremely low. So you can have, this region, what it's saying is that you will have a 95% of suppression of the flux if the cross section is of this order for a particle with this mass. So essentially, it is very simple. Since the particle is very small, then the number density is very, very high. So since the number density is very high, then it doesn't matter that the interaction of the cosmic ray or neutrino is very small. It is going to interact with this huge number of particles that are in the universe. So even if the coupling constant is very small, it is reasonable that you will have a suppression. So from this very simple thing, what we are expecting is that if dark matter is a ultralight scalar field or ultralight boson, the most probably, since we are not observing very anisotropies or caught in the flux, it means that the cross section will be very small and then the coupling will be very small. So from this very simple thing, what you will say is that probably not only the ultralight dark matter is ultralight, but also is very difficult to interact with the rest of the particles. Saying, once we have said that, the question is, what will be the diffuse supernova neutrino background if neutrinos interact with some ultralight dark matter particle? This is something that I did in the morning, so I don't know. But I think that the idea is maybe we can talk a little bit about this. So with this I finish. Thank you very much.
So we have a lot of time for questions.
Hey, I have a question about so what you call star formation rates in one of your first slides when you determine the ratio of core collapse supernova you can form. Yeah, here. So what do you use as a C of M and why is it not dependent on the redshift?
No. So this is the Salpeter initial mass function.
Yeah, but okay. But with the redshift we are, because after you use the star formation rate with the redshift to continue to produce these kind of stars, you continue to use the Salpeter initial mass function.
I see. Now we use.
Because the metallicity is totally different.
You're right.
I'm not expecting at all to have the same kind.
No, it's just, at the end it is just a number. in this case. So probably you're right.
So maybe more than the star formation rate. For me, this function is something more unknown
yes,
than the star formation rate.
probably.
Okay.
I think it was in the same direction that Sebastian. Could you clarify what is because it's not clear for me what is the relation between star formation and large scale structure, I mean cosmology, and supernovae events? Because I mean, star formation rate is not a one-to-one correlation with large scale structure. There are there are a lot of research investigating if the formation, the dark matter evolution is related with the star formation rate. It's not clear, and so you see my point?
Yes, so you're right. So these dots are observationally. So here there are no theoretical prediction, but people have done none. So essentially what they do is take lambda CDM, so take, I don't know, millennium simulation. So you have already what are the points where you are expecting that there will be some galaxies. Then you have to put some physics on that. So you have to put gas, metallicities, and then start to evolve all these things in order to see how many objects are going to collapse in order to form stars, and which size what is the size of this star and so on will depend on the physics that you're introducing. So essentially, nobody has done a full evolution of what is the number of stars that you can form within a evolution of the universe, because you don't know what are the metallicities. You don't know how many supernovas are exploding. You don't know how much the feedback of the supernovas are going to destroy the stars. But you have to do it, because in principle it is something that you are looking forward. So there are two ways of attacking this problem. One is full simulation. So when you introduce some free parameters, and the other one is semi-analytical models. And then you have the interplay between them. So semi-analytical models get benefit from the information that people are getting from the simulation. People from simulation are getting some information about the semi-analytical models. And then between some reasonable assumptions, the prediction of the star formation rate is in concordance with these points. This is amazing. I don't know how many parameters you have to fix in order, probably more than 17, to have this concordance. But in principle, the physics is there, so and people are really hard working on this track. Yes.
So going back to your last question, the idea is how these both Einstein condensate will interact with the diffuse supernova neutrino, right?
Yes.
And we know that the diffuse supernova neutrino flux is going to be measured as soon as that scale. But there's also the possibility to interact, or it will also interact with the Rayleigh neutrinos, right? So the flux is 15 orders of magnitude higher than the diffuse, or maybe even more, 15, 20, and that's another possibility. Of course, those are more complicated to measure, but there are also some ideas.
Yes.
So that's also another possibility. Right?
Yes, of course. Yes. The problem is that the time of detection for that Rayleigh neutrino, right? I don't know if we are going to be able to detect. But if you can imagine how to detect, Stockholm is waiting for you.
You already answered the question. My question was the problem. So what do we need to make a simulation about the models? But I think you already told us a little.
There are many reviews, but I think that it is important to get involved now because, yeah. So we can talk later about some references.
Alexis has a question also.
this, so you show the example how the measurement of the diffuse supernova rate can help you discriminate between cosmologies in a sense. But the example that you were able to clearly distinguish is this volumetric or
logotropic.
The very long name cosmology. But is that more like an academic demonstration that you can, or how realistic is it? I forgive my ignorance about this model. It's probably very far-fetched that you not match many of the constraints that the lambda CDM model does. It fits the data in many different observations. So this is more like a
illustrating. Yeah.
Right. Are there any other closer cosmologies that you could try to see if they're more real?
So, to be honest, most probably is a reasonable cosmological model that fits everything. Most probably is going to predict the same diffuse supernova. This is the honest question. So that's why, but it was randomly. So we saw in the archive logotropic. This one's funny. Let's take it. Viscous, this one, and it worked. So I don't know. The sad part of the history is that we are proposing too many models. And to test them, it's very hard to test them, as we have already said. No, and probably this way is very fast in order to see if it is too crazy.
I have a question. Yes. So it's concerning this 10 to the minus
23
EVs.
Yes.
So in principle, this guy at some point will interact with the rest. I mean, for instance, with the Higgs through the quartic coupling. If it's interacting also with gravity.
So
one thing is to be a Goldstone that is massless, but once you add this mass, how to tune everything to keep it like that?
So the model is very tricky in the sense that this is the Lagrangian. This is the point. This is the point. So it is disconnected of everything except gravity.
Okay, but 10 to minus 21, at some point gravity also will give you corrections, right? Small corrections, let's say.
Probably you're right. So probably it has to do...
Planck scale suppressed, but 10 to the minus 21 is...
So then, yeah, you're right. So essentially, there is a misleading process probably, in the sense that essentially what you do here is
classical.
It's classical. This is the point.
But we are living in something else.
This is the problem. So actually, I agree with you. This is something that we have to think more seriously.
Quantum corrections.
For instance, yes, I think that this is something that it is.
22 is, come on.
No, is the upper bound of the photon. Yes. You're right. Yes. It has been increasing the limit. By some assumptions, yes. 10 to the minus 17, and PDG it is 10 to the minus 17 electron volts, the photon. Yeah, I don't know.
More questions?
I'm sorry, my question it's about your simulation. Sorry, maybe I didn't understand, but which parameters are you using in your simulations for this model?
So what in this model?
Yeah.
Well, actually, the simulations have done in this part. Who did this is a guy who is now in Spain, in Bilbao. The Taiwaneses, I don't know, the Taiwan people. So Ivan knows very well who have done this simulation. Essentially, what you have to do is you take this system. So this is the Lagrangians, and you compute what are the evolution. You put a Freeman-Robinson-Walker metric, and then you will have your Friedman equations. The only free parameter is the scalar field, mass. And then what you do is transformation, which is called the Madelung transformation, which convert in the Newtonian limit this Friedman equation in a Schrödinger-Poisson system. This Schrödinger-Poisson system, after the Madelung transformation, is very similar to a hydrodynamic set of equations. So essentially what they did is they took a code that has some hydrodynamic evolution with these new equations that you obtain from this transformation, and then they evolve with only free parameter, which is the mass. And it is very surprising that at the end you finish with some structure very similar to the lambda CDM, and actually you have more information about that when you have a zoom on the regions of this universe with this scalar field. Then you have a core in the galaxies, let's say, which can be modeled by a soliton, which essentially is this boson star that I said, but it has a tail, which is very similar to a Navarro-Frame-White profile. So the new profile for the galaxies from this simulation is a boson star with a tail of Navarro-Frame-White. So this is roughly what they did. This is not my something I have done, but it will be very nice to do it. Right, Ivan? Ask it.
More questions? If not, let's thank Juan again. And time for lunch.
So that's it for the morning session, and we will come back at 4 p.m., right?